Okay, so the other factor which we're going to consider when we think about pKa is going to be delocalization. So I'm going to give you two examples, and we're going to talk about how electron delocalization actually can affect pKa. So I'll give you two molecules. So this molecule right here is ethanol, and this molecule on the right is your acetic acid. So we've talked about the pKa's for both of these. So let's go ahead and put those down. So the pKa for the ethanol is 15 versus the pKa for the acetic acid is 4.7. So if we think about losing a hydrogen for both of these molecules, so minus H plus here, and then we'll have, minus H plus here as well. After we lose the H plus for both of these molecules, this will be the resulting molecule. So we have a negatively charged oxygen on the left, and for the molecule on the right, we also have a negatively charged molecule. And I'm going to go ahead and draw in all of the resonance forms for this molecule. Looking at these molecules, it's not obviously apparent why the carboxylic acid is so much more acidic than the ethanol. They both have oxygen. They both have oxygens that yield negative charges after you lose an H+. Why is acetic acid so much more acidic? And it all has to do, again, with the stability of the conjugate base. So we know that this acid is way more acidic, so what that must tell us is that this conjugate acid is way more stable than this conjugate acid. So what's happening? So what we can do is, just like by drawing an electron withdrawing group attached to the molecule, we can also show other ways that electrons can have a bigger backyard. So this is going to be an introduction to a little bit different form of electron pushing. And all of these electron pushes are going to happen within the molecule. Everything we've seen up to this point has been electrons flowing from one molecule to another molecule. And these electron pushes are all internal. So what we're going to see is that we can draw electrons flowing from this oxygen to this oxygen to carbon bond. And so if we do this, there are two things that could happen. We could either stay right here, or we can draw another arrow. So let's go ahead and talk about the scenario where we would have just stopped. So if we had just stopped right there, let's go ahead and use this red, and we'll draw the resulting molecule. So in this case, this would be our resulting molecule. Okay, 1, 2, 3, 4, 5, 6, 7. So now, hopefully, whenever I've drawn this, you've seen something wrong right away. So if you think about this carbon in the center, you can start to count the total number of electrons that are surrounding that carbon. So there's 2, 4, 6, 8, 10. And then if you think about that, we've automatically violated a very, very fundamental rule that's never, ever going to go away for the remainder of organic, and that's the octet rule. So in this case, we have 2, 4, 6, 8, 10, where in reality, we're only allowed to have 8 electrons surrounding this carbon. So because of that, this molecule cannot exist. So we can't just stop here. So this is an invalid electron push. So the way we've saved ourselves from making this molecule is we can push one other set of arrows. So right here, we can actually take these electrons that used to be in the pi bond and push them up to the oxygen as a lone pair. Okay, so let's go ahead and draw what we would get from that. So let's draw these arrows, and we would show that the negative charge now lies on the top oxygen, and we would have 2, 4, 6, 8 electrons surrounding this top oxygen. And so now we've saved ourselves from drawing this molecule down below. So at this point, we probably talked about Texas carbon. So we have a Texas carbon down below, which is very bad and no good. And then we freed ourselves from the Texas carbon situation up above. Okay, so in this case, if we compare and contrast the electrons and go back to this metaphor of having a backyard for our dog to run around, in this case, the electrons are stuck very much so on the oxygen. And in this case, what we can do is say that because this negative charge is not necessarily here at the very bottom right, and it's not necessarily here on the very top right, we can say that these electrons are actually delocalized. So let's go ahead and draw what this really looks like in reality. we can draw a situation where we have this molecule right here, we have our two oxygens right here and right here. And what's really happening is that instead of having a double bond here or right here, that double bond is actually in flux in between these two oxygens. And so overall, we would have, still two lone pairs here and two lone pairs here, but now that negative charge is really shared between these two oxygens, and the overall molecule is still negative. And so what we've done is we've set up a mental model for something called resonance. And so what we have here, this little arrow that has one line going left and right and two heads on it, this is called a resonance arrow. And these two molecules, this one on the right and this one on the left, these are called resonance contributors. And this molecule on the very bottom is called a resonance hybrid. And so what this is really telling us, and what you can take from it, is that whenever we draw molecules down on paper, it's not necessarily the whole truth. This molecule on the left isn't really the way that the conjugate base for this acetic acid actually looks, nor is this molecule the real way that this conjugate base really looks. The real reality is, or the actual reality, is some combination of these two different molecules. So both of these molecules describe reality to a certain degree, but neither one of them are the complete truth. This resonance hybrid on the bottom, on the other hand, is a little bit more accurate in terms of how the molecule actually exists in reality. But it's a little bit harder to visualize, a little bit harder to draw, and a little bit harder to stomach. So in general, people kind of stay away from resonance hybrids in terms of drawing them, as long as we can draw one of the two resonance contributors. It's kind of understood that the other one really exists. Okay, and so the arrows that we use to draw these two resonance contributors are pretty specific as well. So if I had drawn, one arrow going this way and one arrow going this way, these arrows would actually be incorrect. These are no good. So these aren't resonance arrows. You have to have just one horizontal line with the two arrowheads going left and right. And I know it's a bit picky, but that's the way that we talk about resonance. And if we were to talk about equilibrium, on the other hand, then you would use these kind of arrows. And it's a very fine distinction, but it's something that we care a lot about.